Okay, so can everyone do the fun problems of the day while we're waiting for more people to come in? If you don't know, for the second part of the fun problem of the day, the big hand is referring to the hour hand, not the minute hand. Okay, so for the first one, so initially the hand is at 7, and then you add another 7, which gives you 14 o'clock. But 14 o'clock isn't a real time, and instead 14 o'clock would be 2 o'clock. So the hour hand's going to be at the 2 in 7 hours. And for the other one, in 25 hours, 25 hours is 1 day plus 1 hour. And we know we can effectively ignore the day because it won't affect the hour hand. So this problem is the equivalence of saying where's the hour hand 1 hour after 8 o'clock, which would be nine at the 9. Okay, so we're going to go over the most missed homework problem, and all of you who submitted the homework, all of you did well. Okay, so this problem is the same as saying which positive integer that's less than or equal to 150 has the largest number of positive factors. That's basically what this is saying. So then you can realize that it would be in the form 2 to the a times 3 to the b times 5 to the c times 7 to the d, so on. Okay, but also 2 times 3 times 5 times 7 equals 210, which is greater than 150, so you cannot have a 7. So it's in the form 2 to the a times 3 to the b times 5 to the c. And so this just means we're adding on prime factors to 2 times 3 times 5, which is 30. And the most number of prime factors out of 2, 3, and 5 that we can add is two twos. So the maximum number, the number with the largest number of factors is 2 cubed times 3 times 5 Okay. So this week we're gonna cover number bases, GCD and LCM, modular arithmetic, Fermat's Little theorem, the Chinese remainder theorem, and we're gonna lightly touch up on Diophantine equations. So first of all, what are number bases? So some common number bases include binary, which is base 2, ternary, which is base 3, octal, which is base 8, hexadecimal, base 16, and the one we've so far been working with, decimal, base 10. So base 10 is what we usually use for our everyday life. And it only has two digits, 0 and 1. It goes 0, it goes 0, 1, 10, 11, 100, 101, 110, and you follow this algorithm that's outlined here. And this is example of another base. And you don't need to know this name, really. Alright, so it goes 0, 1, 2, 3, 4, 5, 6, and 7 goes to 10, 8 goes to 11, 12, 13, 14, 15, 16, 20, 21, 22, 23, 24, 25, 26, all the way to 66, 100. And then it continues on past that. Okay, so here's your first example. And write it in like, suppose 19 base 2 is like 67, and 19 base 7 equals 89, which is clearly false. Then send your answer in this form. Okay, so okay, first of all, base 2. Hold on a second. 19 equals 1. Okay, equals 16. Oh, come on, what? 16 plus y. 16 plus. Oh my god. Oh. Alright, 0 times 8 plus 0. Please wait. Uh, okay, sorry. Plus 0 times 4 plus 1 times 2 plus 1 times 1, which in base 2 is 10011. And now base 7, 19 equals 2 times 7 plus 5 times 1, which is 25 base 7. And if you're wondering how you should easily do that stuff like this, you should first find the, say it's base n. You should first find the smallest, no, you should first find the largest power of n that's less than the number, and you should see how many times it divides into that number, and then subtract it out, and then you just repeat the algorithm for that. Okay, here's another example. Okay, so I'll give a hint for this problem. So let n equal ab base 8, where a and b are variables. Okay, I'll just give another quick hint. So this would imply that n equals 8a plus b. Okay, so then the statement says 8a plus b plus 5 times a plus b equals 8b plus a. And so 13a plus 6b equals 8b plus a. So 12a equals 2b. And the only solution to possible to this is a equals 1, b equals 6. So n equals 16 base 8. And if you check this, 16 plus 7 times 5, 8 plus 6 times 7 plus 5 equals 49, which is 61 base 8. So n is 16 base 8. Alright, now on to the GCD and LCM. So first of all, the GCD, it can also be called a GCF, which both mean the same thing. And it's the largest number that can divide all of the numbers that you're doing it of. It's usually just of two numbers, but you can do it for as many as you want. The GCD is usually written as GCD of AB or in parentheses A, comma B when the context is clear enough. But don't just randomly go around writing it in parentheses A, comma B. So, an example, the greatest common divisor factor of 12 and 16. So, here are the lists for 12 and 16. And as you can see, they repeat in 1, 2, and 4. And the largest of those is 4. Note how all the other common factors divide the greatest common divisor. And now, the least common multiple. It's the smallest number that is a multiple of all the numbers. Also, it's also usually just used for two numbers, but you can also apply this to as many as you want. So here's two examples. So the first example is of 3 and 5. 3 is 3, 6, 9, 12, 15, and 5 is 5, 10, 15, and the smallest is 15. And another example is for 4 and 10. The multiples of 4 go 4, 8, 12, 16, 20, and the multiples of 10 go 10 and 20. So this is their least common multiple, which is 20. And here's a theorem. The LCM times the GCD of A and B just equals AB. And one method for determining the GCD is by prime factorizing the two numbers. For example, like 2 times 3 times 7 and 3 times 7 times 11. So their GCD is the smaller of the two exponents for each of the prime factors. So there's a 2, 0 here, and an 11 to the 0 here. So their GCD would be 2 to the 0 times 3 to the 1 times 7 to the 1 times 11 to the 0, which is 3 times 7. And the LCM is similar, except it's the larger of the two exponents when you prime factorize it. Okay, the Euclidean algorithm now. And this is a specific way to find the greatest common divisor of two integers. It works better when they're big because this helps you make them smaller. Yeah, so like using this, it's not hard to find GCD of this, and it's not too hard to find the GCD of this. Whereas if you prime factorize this, it could be very nasty. So here's basically how it works. So for a smaller example, GCD of um, 112 and 42 as shown here. And so the first step of the algorithm, simplify this to 42 and 28. And this goes to GCD of 14 and 28, which is clearly 14. Okay, now here's an example. If you want to, you don't have to explicitly find what the LCM is. You can just like use Sorry, okay, I'll address the GCD part first, and then I'll give you some more time to work on the LCM. Okay, GCD of 1254 240 equals GCD of 54 knock 240 and 54, and this equals GCD of 54 and 24, and this is clearly 6. So the GCD is 6. Actually, I'll go into a bit more detail here. Okay, so equals GCD of 1254 minus 5 times 240, comma 240, equals GCD of 240 and 54 equals GCD of 240 minus 54 times 4, comma 54 equals GCD of 24 and 54. And at this All right, so for the LCM, we're going to use this fact. So the LCM equals 1254 times 240 over the GCD, which we know to be 6. And if you multiply this out whatever way you want, this is what you'll get. Okay, now here's another example. You can just abbreviate the days to be like sun, mon, Tues, Wed, Thurs, Friday, and Saturday. You don't have to fully write them out. Please don't troll when you're sending answers in. Okay, I'll start explaining. So, 919 days. A week before this is 912 days, and you can continue this so on. I believe 130 times, which gets you 2 days. So, and 2 days after Thursday is Saturday. So the answer is Saturday, or however you want to abbreviate that. Okay, on to modular arithmetic. So when we divide two numbers, we have an equation that looks like this. Okay, that's bad. Here, where A is called the dividend, B is the divisor, Q is the quotient, and R the remainder. Sometimes all you care about is this. In that cases, there's something called the modulo, often abbreviated as mod. So using these numbers, you have that A mod B is congruent to R, where congruent is written as this. So an example, easy example is what is 7 mod 2? And so you can look at it this way. Okay, let me change the color. So 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6, and 6 to 7. And so 7 mod 2 is 1. And now negative 5 mod 3. You can do this a similar way. 1, 2, 3, 4, 5. Another way you can calculate A mod B is just by subtracting or adding out multiples of B until you get something in the range 0 to B minus 1. Okay, so some basic properties about the modulus relation. So first of all, it's reflexive, which basically means A is congruent to A mod B. And it's also symmetric, which means that if A is congruent to B mod M, then B is also congruent to A mod M. It's also transitive, which means that if A is congruent to B mod M, then B is congruent to C mod M, then A is congruent to C mod M. And if A is you can read these for yourself. Hey, some divisibility rules. So these rules let you test if one number is divisible by another without being able to do much, without needing to do much. So it first of all, is 723 divisible by 3? So you can try doing the long way, or you can use the rule. And 7 plus 2 plus 3 equals 12 is congruent to 0 mod 3. So the answer is yes. And so try applying the divisibility rule for 9 here. Note that 3 and 9 are special cases where the sum of the digits is congruent to the remainder of the number itself mod 3 or 9. Okay, I'll just go over this now. So 1 plus 2 plus 3 plus 7 equals 28 is congruent to 1 mod 9. So this is congruent to 1 mod 9. Now, for Moth's little theorem, this is just a little side thing that could be useful in near the late AMC8s. So it basically says this, and I won't go into the details of a proof. Okay, so here's an example. Okay, sorry. This should be 11 to the 12th power. Okay, so you should know by now that you should know that 13 is prime. So we can apply Fermat's little theorem here. And in this situation, a equals 11, and the remainder is just 1, obviously. And fun aside is that Fermat's little theorem is a special case of Euler's totient formula, and that and this is a special case for prime p. But you don't need to know that. Okay, Chinese remainder theorem. So you can read this by yourself later. It's basically just saying for a series of congruences, if all of the mod that you're taking it of are relatively prime to each other, then there is one exactly one unique solution to its mod of their product. Like say 1 mod 2, 3 mod 5, and 6 mod 7 has exactly one unique solution mod 105. And that unique solution is guaranteed to exist and be unique by CRT. Okay, so here's your example. Okay, so clearly you just want to find the least common multiple of all of these numbers and then add 2, and the least common multiple of 3 and 4 is 12. Okay, so 3 and 4 is 12, and this takes care of 6. And the least common multiple of 12 and 5 is 60. So the answer is 60 plus 2 equals 62. Now, onto Diophantine equations. In these equations, we don't care about most solutions, we just care about the integer solutions. So the very simplest form of a Diophantine equation is linear and is basically ax plus by equals c, where a, b, and c are given. And here's an example of a set of linear Diophantine equations. And Yes, you can uniquely and yes, there's exactly one possible answer to this. There is not multiple, even though it may seem like not enough information. There's enough information. Okay, so let there be x pennies, y nickels, z dimes, and w quarters. So this gives you the equation, the this pair of equations, and you're also given this for the restriction. So one way you can do this, is by taking the difference of the above two equations, which leaves you with this. And so 9z equals 93 minus 4y minus 24. So z equals 93 minus 4y minus 8z minus 24w is congruent to 1 mod 4. But you also know that you can't have 9 dimes, otherwise you can't have at least 1/4. So then z equals 1 or 5. And now, continuing here, if z equals 5, then you have that 4y plus 24w equals 48, or y plus 6w equals 12. So then 6 must divide y, so y must equal 6. However, you also know that y is 9 minus x minus z minus w is less than equal to 9 minus 1 minus 5 minus 1, which is 2. But you also know that if 6, which is not less than or equal to 2, so then z equals 1. And okay, so and then past here you can find the rest. So for example, this directly gives that x equals 2 and y plus 2z plus 5w equals 20. So y plus 5w equals 18. And so this forces out y equals w equals 3. Yeah. Okay, now the chicken McNugget theorem. It states basically that for any two relatively prime positive integers m and n, the greatest integer that cannot be written in the form am plus bn for non-negative integers a and b is mn minus m minus n. And here's an example of the chicken McNugget theorem. It's called the chicken McNugget theorem. It's called the chicken McNugget theorem because apparently one story of its origin was that people from McDonald's wanted to find out what was the largest number of chicken nuggets that couldn't be made with the given sizes. Oh, right. And for here, ignore this. Instead, just do okay, largest that cannot be. Okay, largest that cannot possibly be the total number of people, horses, sheep, chickens, whatever. Okay, if you want, you can instead. Okay, so here's the choices from the original problem. but I think I also kind of revealed that the answer is actually the largest the largest that you can't achieve. Okay, so let there be H horses. Come on, H horses. Then there's 3H people and 9H ducks, which is 13H for this. Now, let there be C cows. Then there's 4C sheep, which makes a total of 5C of these two species. So the the number that's possible is this, and using the chicken McNugget theorem, the largest that cannot be achieved is 65 minus 18, which is 47, which conveniently is one of the choices. And now here's an exercise. Okay, so it has 5 Mondays, which means that Monday is the first, second, or third day of July. If it's first, then August has five of Thursday, Friday, Saturday. If it's the second, August has five of Wednesday, Thursday, and Friday. And if it's the third, August has five of Tuesday, Wednesday, Thursday. And the only one that appears in all three is Thursday, D. Okay, here's your excerpt for the first one. Here's your first exercise. Okay, so xy base 10 is, come on, 10x plus y. And if we reverse the digits in base 16, that equals 16y plus x. So 9x equals 15y. So x equals 5 thirds y. And you know that x is less than 10. So the only possible solution is x equals 5 and y equals 3. So the two-digit decimal number is 53. And here's your next exercise. Okay, so this problem basically wants us to compute an x such that 100x is congruent to 160x is congruent to 200x mod 800, which is also congruent to 0, but that's not the important part here. So you can divide out 20, and that simplifies this to 5x is congruent to 8x is congruent to 10x mod 40. So for 5x, it's congruent to 10x to be true. For this to be true, you know that x is congruent to 0 mod 8. Now, you also have that 8x is congruent to 0 mod 40, so x is congruent to 0, come on, erase, 0 mod 5, so x is congruent to 0 mod 40. And we can check that this is true by seeing that the runners need 4 minutes, 5 minutes, and 8 minutes, respectively, in reverse order to run a full lap. And in 40 minutes, and their LCM is 40 minutes. So here's your next exercise. Okay, so a little hint is that the next time all three meet is 990 days, and okay, and clearly they won't meet every day. Okay, so LCM of 18 and 22 equals 198. So this is 4 days in common for A and J. For A and C, LCM of 15 and 18 is just 90, which is a total of 10 visits, 10 meets. And J and C, LCM of 15 and 22 equals 330, which makes a total of 2 days in common. So 10 plus 4 plus 2 equals 16. And you know that none of these overlap because the only way they'd overlap is if all three meet on the same day, but we calculated that to be in 990 days. And none of these are at 990. So the answer is just 16. Okay, here's your next exercise. Okay, so 31 is congruent to 3 mod 7, and so days that are within 3 days before Tuesday, Thursday, etc. So Saturday, Sunday, Tuesday, and Wednesday are all bad days because it's 3 mod 7. So the only possible days that are good are Monday, Wednesday, sorry, Monday, Thursday, and Friday. Because, okay, because this adds to both of them, and these two don't affect Monday count. So, 3 of the days. Okay, and thank you for coming to today's class. Th- And thanks to my brother Gordon for being my TA. And the handout video and the video of this class will be uploaded to the classroom soon. And yeah, I guess you can leave now. Bye.